Right, today we're going to look at a continuation of the use of a balanced equation. In fact, we're picking up from chapter 8. We backed up into chapter 6 and 7 to get a feel for chemical reactions. And in fact, we left off with chapter 6 with this term, stoichiometry. And now we're going to get into using the methods of stoichiometry in this chapter, chapter 9, chemical quantities. And chapter 9 is the only chapter in, for exam 5, chemical quantities. At this point, we've learned our alphabet. We've learned how to write words in chemistry, chemical formulas. And that's where we left off in chapter 8, using those chemical formulas to determine the composition of compounds. And then we learned how to balance equations. And now we're going to use those equations to provide useful information about the outcome of the reaction itself. And that's where stoichiometry comes in. All right. So just as a review, when we write a balanced equation, such as, let's say we're going to combust hydrogen with oxygen and produce water. Okay, we know that that's not balanced because, for instance, 2 oxygens here and only 1 there. So if we put a 2 here and a 2 there, now we have a balanced equation. Well, what can you do with that balanced equation? That's the topic of chapter 9. But examining the equation, we can look at it in 2 different ways. We can look at it as individual atoms and molecules, like 1 molecule of hydrogen. It's diatomic hydrogen element. 2 molecules of that will react with 1 molecule of oxygen gas, which is also diatomic, and the product will be water. And this is an exothermic reaction. It gives off a lot of heat. So there's enough heat there to vaporize the water. It stays in a vapor. And we get 2 molecules there. So the ratio in this reaction is 2 hydrogens, 1 oxygen gives 2 waters as individual molecules. But we can also look at it in terms of the macroscopic. That was the microscopic interpretation. The macroscopic interpretation says that the relative number of, pause for a second. Okay. The macroscopic interpretation is that of moles of. That is, 2 moles of hydrogen gas will react with 1 mole of oxygen gas to give you 2 moles of water. Now that's something we can get a handle on because a mole is very large. 6.022 times 10 to the 23rd things is a mole. So that's 1 mole, just 2 times that would be this quantity. And these ratios, as written, are stoichiometric. We'll call them stoichiometric. In other words, exactly 1 mole of oxygen and exactly 2 moles of hydrogen. And that's what the coefficients stand for. We can look at them at the microscopic level or the macroscopic level. And for practical purposes, the macroscopic interpretation allows us to do the stoichiometric calculations. So here's another reaction where we have 1 mole okay, 1 mole of ethanol. That's alcohol, the drinking kind. And we can combust it with 3 moles of oxygen to produce carbon dioxide and water. Now, for simplicity's sake, we've left out the phases, right? Under some circumstances, the phases don't matter. Under other circumstances, the phases do matter. But for our arguments here, we're leaving off the phases. All right. So we know this equation is balanced because we can count up the number of carbons, say 2 carbons here, 2 carbons there, 6 hydrogens here, 6 hydrogens there, 6 oxygens, 6 plus 1 is 7 oxygens, 4 oxygens here, and 3 there is 7. So we know it's balanced. All right. And there you're given the microscopic versus the macroscopic interpretation. Okay. So here's another equation. And we're told that it's not balanced. Plus, let's see, we're given phases here. So we're going to put the phases in. Leave a little gap for coefficients when we balance the equation. Plus SO2 gas. Okay. Now, if we were to balance this equation using our budget method, remember, well, first of all, let's name these compounds just as practice. Okay. This is going to be a 2 minus, a 2 minus. So this would have to be, one of these would be 2 minus, this would be a plus 1. And this would also be a plus 1. So this would be copper, copper 1 sulfide. And notice the sulfide has an F, not a pH. On this side of the ocean, we use F instead of pH. So if you write in copper 1 sulfide with a pH, that means you've looked it up somewhere and you haven't used your brain to create the name from the compound. This one would also be copper 1 oxide. Okay, and that's copper. This would be sulfur dioxide, type 3 compound. It has both nonmetals. So this would be sulfur dioxide. There we go. So those are the names of our compounds. Now we're going to balance the equation. So we use our budget method. We have copper, we have sulfur, we have oxygen. That's it. Those are all the elements. So on this side, we have 4 coppers, we have 1 sulfur and 1 oxygen. And on this side, we have 1 copper, we have 1 sulfur and 2 oxygens. Okay. So we want to keep the copper till last. So we're going to start someplace else. We'll start with the oxygen. So we have 2 oxygens there. We need 2 oxygens here. That gives us 2 oxygens. Now that gives us 4 plus 2 is 6 coppers. Okay. So if we put a 6 in front of that copper, we get 6, 1, 2, and that equation is balanced now. Let's see, let's remove. These can get in the way, so let's remove those. Right there. Okay, now we have a balanced equation. We can do something with it. Okay, so this is a concept check. So we're saying how many dozen copper atoms could be produced from a dozen molecules of sulfide and 2 dozens of oxygen, oxide of copper 1. So we're given, we want dozens of copper atoms. Okay. How many dozens of copper atoms could be produced from a dozen molecules of sulfide, a sulfide of copper? So this is 1 dozen. And 2 dozen copper 1 oxide. So 2 dozen. So notice that the ratio here is 2 to 1. This is a stoichiometric ratio. That means that this would be 6 dozens. Also, how many moles of copper could be produced from 1 mole of sulfide and 2 moles of oxide? Well, if we just put that, substitute a different unit in there, we still have the same ratio because these are references to numbers of things. 2 moles, 2 dozens. The different sizes, but we're still referencing numbers. So 1 mole of copper 1 sulfide plus 2 moles of copper 1 oxide will produce 6 moles of copper metal. Okay. This reaction here is the reverse of the one I gave you earlier, where hydrogen was combusted with oxygen to produce water. We can also take water and split it into hydrogen and oxygen. It's just the reverse of the previous reaction. Let's see, I'm gonna have to fix that in just a second. Do a little board maintenance. Here we go. Okay. So this equation is balanced for the decomposition. That's the equation type here. Remember from the chapters 6 and 7, we're decomposing water into hydrogen and oxygen. So we can predict the number of moles of product that the reaction will yield if we know what the mole ratio is for each of the reactants and products. And that's what the coefficients tell us. This decomposition will produce 2 hydrogen moles. From 2 moles of water will produce 2 hydrogens and 1 oxygen. In terms of moles. All right. And the ratio is fixed for this balanced equation. So if we say instead we have 4 moles of water, how many moles of product will it produce? Well, the ratio is 1 to 1 here, 2 to 2. So it'd be 4 moles of hydrogen and two moles of oxygen. Now, when we're doing stoichiometric calculations, what we can say mathematically is that 2 moles of water equals 2 moles of hydrogen. And the reason I write it that way is because we know that if we have an equivalence, that can be converted easily into a conversion factor. So what I'm saying here is that the ratio of these two, either 2 moles of water for every 2 moles of hydrogen, can be used as a conversion factor if we start off with, say, 6 moles of hydrogen. Then numerator, denominator, that cancels, and now we have 6 moles of water, right? Using our procedures we learned earlier in the semester for dimensional analysis. Right? We have used this relationship here, derived from the equation, to give us a conversion factor. And that's going to be important when we try to deduce the outcome of a reaction. Okay. So let's change equations. Now we have sodium hexafluorosilicate. And here we are. Sodium hexafluoro. I put the silicon first. Hexafluorosilicate. And sodium will yield what? Well, it yields silicon, pure silicon, solid, plus 6 sodium fluorides. Okay. We check to see if that's balanced, and it's not balanced because I left that term out. So 6 fluorines, 6 fluorines, 1 silicon, 6 sodiums, 6 sodiums. Now it's balanced. So the question is, how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted? 3.5 moles of sodium is reacted with excess sodium hexafluorosilicate. All right, the reason we say this is excess is because, and we're going to look at this a little later, because of the concept of limiting reactant. The reactant that runs out first. In other words, if you have a stoichiometric ratio, say if we had 4 moles here and 1 mole there, that would be stoichiometric. So they would both be consumed together, and they would all disappear, and we produce products. But if we know a certain amount of a reactant, and we give an amount of the other reactant that's not stoichiometric, then one of them is going to run out first. So to alleviate that problem for now, we say that this reactant is excess. In other words, there's plenty of it. It's like lighting a candle in the room, right? Eventually you'll run out of wax as the candle burns down, but you'll never run out of oxygen because there's plenty of oxygen in the Earth's atmosphere to consume that entire candle. The oxygen is in excess. This is excess. So we only need to focus on this one, using all of this to produce that. Okay. So we want to determine the number of moles of sodium fluoride that can be produced by this reaction. Okay. We do have a balanced equation. That's confirmed. And we know how much we're starting with. So this is actually a dimensional analysis problem. If we have 3.5 moles of sodium, we want to convert that to moles of sodium fluoride. Right? So how do you do that? Well, you want to keep this one so it goes up here. And you want to cancel this one so it goes down here. Okay, so that cancels this one and leaves us with that one. What's the ratio though? The ratio is determined, this conversion factor is determined by the coefficients of the balanced equation. Sodium fluoride is 6 and sodium is 4. So we take 6 times 3.5 and divide it by 4, and that gives us our answer. There you go. 5.25 moles. So earlier in the semester, when we were learning how to use conversion factors and dimensional analysis, we were not just spinning our wheels. We were learning a useful skill that would be that would allow us to continue with this concept. So if you're still weak with conversion factors, go back and drill them. Learn how to use conversion factors. All right. Propane, C3H8. Is a hydrocarbon. And yes, propane is what some people use to heat their homes, to cook their meals, and a lot more people use them to barbecue steaks and chicken on the grill. Propane, under pressure, is a liquid at room temperature. But that doesn't matter for this reaction, of course. But when you ignite it in a burner, you're combining propane with oxygen. And typically when you burn hydrocarbons in oxygen, you get carbon dioxide and water. And 4 waters. Okay, so that's 8 hydrogens on that side and 8 on this side. 3 carbons, 3 carbons. We have 6 plus 4 is 10 oxygens. 10 oxygens. So we confirm that this equation is balanced. Now we want to predict how many moles of carbon dioxide, okay, will produce from 3.74 moles of propane. And I suspect excess oxygen, yes. We're in the Earth's atmosphere, so there's no shortage of oxygen. Okay, so how do you do this? Well, we have the balanced equation. Where do we start? We start from here. 3.74 moles of propane. And where do we want to end up? We want to end up here with moles of carbon dioxide. Well, we need a conversion factor that will cancel and give us that. Now I left out moles because they're going to cancel anyway. So the ratio here is 3 to 1. Okay, so this cancels, that cancels, leaves us with carbon dioxide. And 3 times 3.74, let's see if I can do that. Let's see, that's 12, carry the 1, 3, 21, 22, carry the 2, and 2 and 9 is 11. Okay. I should round that off to 3 places though, because of the significant figures here. Okay. So rounded off, it's 11.2 moles of carbon dioxide produced from this reaction. All right. So we've taken one step further toward determining the actual outcome of a reaction. 11.2 moles doesn't tell us much as a practical matter because we don't measure things in moles. That's required for the calculation, yes, but we measure things in terms of mass and volume and other factors that can be determined easily in the laboratory. But we don't have measurements for moles of things because we can't count things that small. So the next step is to go from moles to mass. Okay. These are just steps we've already done, balance the equation. Now we convert any masses that are given for the reactants or products to moles. And the reason we do that is because this equation is written in terms of moles of reactants and products. 1 mole of this, 5 moles of that, 3 moles of that, and 4 moles of that. It's not written in terms of mass. So if you're given a problem where your starting materials are mass, you have to convert to moles. So there again, earlier in the semester, we learned how to write equations because write formulas for compounds, because if you don't know the formula for the compound, you cannot convert mass to moles. We're talking about molar mass for the compounds. If you cannot write the compound, you will not be able to determine the molar mass for that compound. But once you can do that, then that will allow you to convert any masses that are given to moles. Then we can proceed with our solving the problem. I will say this, once you have the balanced equation, you can imagine great walls. There's a wall here at the arrow. There's a wall at any of the plus signs. And if you start from any one of these positions, you cannot move anywhere in that equation unless you have moles. If you have mass, if you have volume, if you have any other measurement, you can't move. You're stuck. Until you have moles, then you can move and determine the outcome. Okay. So we're going to do an example. Stoichiometry is as we left off in chapter 6, at the end of chapter 6, it's a method for using a balanced equation to determine the relative masses of reactants and products to one another from a reaction, a real reaction situation. Okay. And we're going to look at limiting reactants here in just a minute, but we want to get some experience doing stoichiometry with masses first. So here's an example. Different equations. So let's get the balanced equation up here first. All right. So we have chromium metal. We're reacting it with oxygen gas. And it produces chromium-3 oxide, which is also a solid. Okay. First of all, is that equation balanced? We've got one chromium. Oh, we got two chromiums there. We got 3 oxygens and only 2 here. So we need to balance the equation. Now you can use the budget method and it works just fine. But this is a very simple equation and we should be able to balance it since these are elements. It should be easy to balance. All we need is, let's see. Well, we have to use the trick. We've got an odd number here and an even number here, right? So if we put that 3 over here and a 2 over there, now we have 6 oxygens and 6 oxygens with 4 chromiums. Okay, so set up your budget if you want and confirm that I'm not pulling your lariat. Okay, how many grams of chromium-3 oxide? Okay, can be produced from 15 grams of solid chromium and excess oxygen. Okay, that's everything that's given in the problem. Okay, what's the next step? Well, after you balance the equation, then you notice that you've got mass here, not moles. So you must convert mass to moles before you can move anywhere in that equation. And that's our next step. We need the molar mass for chromium to convert this 15 grams. Right? Conversion factor, grams cancel, leave us with moles. And the molar mass of chromium, I want to use, see, is it 52? Let's see, let's check. Yeah, round it off to 2 places. It is 52. So 52 into 15 will tell us how many moles of chromium we have. Okay, we'll get that one in a minute. Here we go. There we go. That converts now we know how many moles of chromium we're given. At this point, you don't need the coefficients yet. You're given 15 grams of chromium, you just convert it to moles of chromium. Once you get moles of chromium, then you can convert moles of chromium to chromium-3 oxide. Right? So the ratio here is 4 there, 2 there. Right? So, and that cancels this, leaves us with that. So we take half of that value, 0.144 mole of chromium-3 oxide. Now we can convert back to mass. Okay, that should be on the next slide. Here we go, 152 grams. So now we're going to convert this by saying for each mole of chromium-3 oxide, you have 152 grams. That cancels the moles, leaves us with grams. And we should get 21.9 grams of chromium-3 oxide. Okay, that's how you do stoichiometry. You convert mass to moles, then moles this to moles that, and then back to mass. That's what I mean by that great wall. If you don't have moles, you can't move, you're stuck. Well, that's everything in one conversion string. But we did it stepwise. We did this step, and then we did that step, and then we did the third step to get our answer. Okay. I've got a different equation here. So for this one, we're told that 10,2 fluoride is added to some dental products to provide fluorine, right, for dental health. And this is the equation that produces that 10,2 fluoride. So 10 solid plus fluorine gas yields 10,2 fluoride. And that's it's in an aqueous solution. Excuse me, it's an HF. Pardon me. 2HF aqueous. And this is aqueous. And it evolves some hydrogen gas. Okay. That should be balanced. 1, 2 of these, 2 of those. Yes, our equation is balanced. How many grams of 10,2 fluoride can be made from 55 grams of hydrogen fluoride? That means this would have to be excess. You have plenty of tin metal. All right. So we're given mass, but we want to end up over here. So we've got to go to moles. That means 55.0 grams of HF is how many moles? Whenever you see grams and moles in a quotient relationship, think molar mass. So the molar mass of HF is 1.01 for the hydrogen and 19 for the fluorine, 20.01. Okay, so grams cancels, that gives us moles. Okay. I could let the slide do the calculation for me, but sometimes I like to practice myself. So we got 55 and divide by 20.01. And I get 2.7486 moles of HF. Now, why did I keep so many decimal places? Because all of our conversions here are going to be multiply, divide rules. And if I keep extra decimals until I get to the end and then round, I avoid rounding errors for intermediate steps. If we were to string these out and do them all in one calculation, then that wouldn't be a problem. But if we're doing it step by step, then I'm going to keep that many moles of HF. Now we need to convert to 10,2 fluoride. Numerator, denominator. Numerator, what's the ratio? Well, 2 of these and 1 of those. So I need to take half of that. 1.3743 moles of 10,2 fluoride. Okay. Now we can convert back to mass. We went to moles there, moles there. Now we go back to mass. Moles are going to be on the bottom because we want to cancel moles and leave us with mass. So we need the molar mass of 10,2 fluoride. We look up 10 in our periodic table, which is 118.71. 118.71 for 10, and 2 fluorines. 2 times 19. Okay. So that's 38 plus 118.71. This is 156.71. Times 1.3743 is 215.3686 grams. Okay, now we can round it to three significant figures. So that means 215 grams of 10,2 fluoride. There you go. That, this one and the previous example were examples of stoichiometry for mass conversions. Mass one side, mass the other side. Now, as a practical matter, what if we had said, we want to produce 215 grams of 10,2 fluoride? How many grams of hydrogen fluoride would it take, or hydrofluoric acid? We just do the same calculations and go backwards. All right, so you can go either way. If you want this outcome, you can figure by this method how much of this you need. We can also say how much metal was actually consumed. Right? We can, once we convert to moles here of HF, we can use the conversion factor 2 to 1 and convert to that many moles of tin. And then take the molar mass of tin and find out what mass of tin was actually used in the production of this much 10,2 fluoride. So you've got as many possible conversions as you do possible conversion factors. So if we have 1, 2, 3, 4 coefficients, any combination of those two, like we can have 1, 2, 3, 4, 5. We can have 5 conversion factors. Well, actually, you can have 10 because you can flip them, right? Conversion factors are always equal to 1, right? So if you have it this way, numerator, denominator, put it the other way, it's still equal to 1. Okay, another example. How are we doing? Oh, we're good on time. Let's see. Yep, we're good on time. Consider the following reaction. Phosphorus trichloride plus water yields phosphorus acid. We assume this is an aqueous solution because there's lots of water there, right? At least 3 moles of water, plus hydrochloric acid. So what mass of water is needed to completely react with 20 grams of phosphorus trichloride? Well, the equation is balanced, I believe. PCl3 plus 3 water yields H3PO3 plus 3 HCl. And we check to see, and it turns out it is balanced. Okay, the question is, what mass of water is needed to completely react with 20 grams of phosphorus trichloride? All right, you still have to go from here to moles. And that little n is my symbol for moles. So we need 20 grams here. We need to convert to moles. Like that. So what's the molar mass of phosphorus trichloride? Well, phosphorus is 30.97 grams per mole, and 3 chlorines, 3 times 35, 45. Okay, so 35, 45 times 3 and plus 30.97 is 137.32. Divide that into 20. And I get 0.1456 moles of PCl3. Now we want to convert that to moles of water. So we want water on top and PCl3 on the bottom. And the ratio now is 3 waters for 1 PCl3. So I just multiply this times 3 and I get 0.4364 moles of PCl3. Oh, excuse me. No, I don't. Water. There we go. Now we can convert that many moles of water to grams of water. Like that. So what's the molar mass of water? We've done this so many times. It's 18.02. So I get 7.8736 grams of water. We go back to 3 significant figures. So now we have 7.87 grams. Should be our answer. Okay. There it all. That's all these calculations in one string. $7.87 grams. Okay. All right. Let's up the ante a little bit and use what we've learned to solve a more challenging problem. All right. We're given this equation where X represents an unknown element. We know the stoichiometry that in which we react this element with a diborane. And this is a solid. Yields B4X3, okay, plus 3XO2. Okay, that is supposed to be a balanced equation. What are we given? 175 grams of X. Okay, reacts with diboron trioxide to produce 2.43 moles of this compound. What's the identity of X? Well, how do we identify an element? Well, there are 2 ways. The definitive way is the number of protons, right? The atomic number. But I don't think we can get that information from this, from the problem as presented. So our second approach is to calculate the molar mass of the compound, and it is, for most elements, it's a unique value. There are only a couple of places in the periodic table where the molar masses come very close to each other for elements, and then you need a tiebreaker. But for the most part, if we can determine the molar mass of the element, we can discover its identity. So what do we mean by molar mass? Well, I abbreviated MW. We need the mass per mole. We have the mass. What we need to find out is how many moles is that? Okay. Well, we know the moles here, 2.43 moles of B4X3. And we know the mole ratio to be 6 here and 1 there, right? 1 there, 6 here. So we can determine the moles of X simply by this conversion factor. 6 times 2.43. 15.58 moles of X. So now we can put in the mass, grams per mole. Do that calculation. And I get 12.0 rounded off to 3 places, right? 3 places, grams per mole. So what element comes close to that? Go to the periodic table, and you find that the closest element to this molar mass is carbon. Okay? And the animations may give it, yeah. So we have that many moles of X. And then we set up our molar mass calculation, and we find that it's 12 grams per mole, and that's carbon. Okay? All righty. Let's see. What's next? Okay. Now we're going to get into a discussion of limiting reactants. I've given you the definition of a stoichiometric mixture, but for clarity, let's reemphasize that. A stoichiometric mixture is one in which the moles of the reactants are exactly in the same ratio as the coefficients of the balanced equation. So in this case, if we have 1 mole of nitrogen reacts with 3 moles of hydrogen, a stoichiometric mixture would give us that same ratio. 1 nitrogen for 3 hydrogens, or 2 nitrogens and 6 hydrogens, or 3 nitrogens and 9 hydrogens. That would be a stoichiometric mixture. Okay, and this is the artist's rendition of what that would look like on a microscopic scale, right? 1 nitrogen, the big blue balls, the double blue balls, and then the small light blue balls are hydrogens. So for each 1 of the nitrogens, you have 3 of the hydrogens, and it looks like everybody's got partners, right? Every nitrogen has 3 hydrogen partners. That reaction would give us, for each one of those groups, those dancing partners, we would get 2 ammonias. That's a stoichiometric mixture. Now, as a practical matter, can we be sure that measuring out the amount of nitrogen and hydrogen to put together, that we can be accurate enough so that we can actually produce a stoichiometric mixture? The simple answer is no, we can't. Experimental error will never allow us to produce exact stoichiometric mixtures. So this is a theoretical position. In reality, what we get is some error in one of the others. In this scenario, we have too much nitrogen, right? See those extra 2 nitrogens there don't have partners. They don't have any hydrogens for them. So that means the nitrogen is in excess. In this scenario, nitrogen's excess. So what does that make hydrogen? Hydrogen is limiting. So what do we mean by limiting as a practical matter? Is that in this reaction where you have nitrogen plus 3 hydrogens yields 2 ammonias. When hydrogen runs out, the reaction stops. There's no more hydrogen to react, so you can't have a reaction. That's what limiting means. And we still have those nitrogens in the mixture, the product mixture. We have ammonias, but now we have nitrogen in excess. It's left over. Okay. Hydrogen runs out first, leaving nitrogen excess. In order to conduct this type of stoichiometry, we've got to determine which of the reactants is limiting. Now, to keep things simple, when we're discussing limiting reactants at this point, we're going to have only 2 reactants. But in reality, you can have any number of reactants depending on the reaction being studied. You could have 3, 4, 5, 6, but always one of them will be limiting. Now, sometimes it's limiting because we can't accurately produce a stoichiometric mixture. But other times, and very often, a reactant is limiting because we set the reaction up that way. We say, we're going to make everything else excess, and this reactant is limiting. Okay, so we could do that. We could say, all right, we're going to limit the extent of this reaction by making this one excess. We know it's excess. We know what the stoichiometry is. So we can set it up so this one is excess. That means we know when the reaction will run out. When hydrogen will run out, that's limiting. That gives us some control over the outcome. All right, so here we have a reaction in which methane, CH4, is reacted with water. And this occurs at a high temperature, by the way, to produce hydrogen gas and carbon monoxide. This is one way that hydrogen is produced for things like, say, fuel cells. Rather than splitting water into hydrogen and oxygen and getting hydrogen as a product, we take methane, which is natural gas, and react it with steam at a high temperature and produce hydrogen. Then we extract the hydrogen and it goes into another stream. But back to the problem at hand. This is our reaction. A stoichiometric mixture would say that we have 1 mole of these, 1 mole of those, and we get 3 moles of hydrogen and 1 mole of carbon monoxide. So what we're seeing there is no, we're not seeing. This is not stoichiometric. Notice. This is 1 to 1. So if we have 1, 2, 3, 4, 5, in this case, we have 5 moles or 5 molecules of methane, but we only have 3 water. So which one is limiting? This one. It's 1 to 1. So for every 3 of these, there should be 3 of those. We're going to have 2 moles of methane excess, and the water is consumed. But knowing this, we can also say that for 3 of these, we'll produce 9 of these and 3 of these. Right? 1 to 3 to 1 is 3 to 9 to 3. So that would produce, since this is limiting, that this determines the outcome. Okay, there it is in black and white and blue. Water is the limiting reactant. Methane is excess. Okay, so a limiting reactant problem is solved similarly to other stoichiometries. We have to write the balanced equation. Actually, the step before that is write the compounds correctly. Then balance the equation. Then if you have masses, convert them to moles. Then convert the number of moles of reactants to the number of moles of products based upon which one of the reactants is limiting. So we have to determine the limiting reactant. And that's before you actually convert moles to mass. You have to know what is the limiting reactant. Now, as a practical matter, say you have a given mass, like X grams of this and Y grams of that. How would you proceed? Because you're not told how many moles. Okay. Well, convert to moles of water, and convert to moles of methane. Okay. Then say convert moles of water. Say we want to find out how much hydrogen. Convert that to moles of hydrogen. Then convert this one to moles of hydrogen. Okay. Now, which one's limiting? The limiting one is the one that produces the fewest moles, the fewer moles of hydrogen. So if water is limiting, then this value will be less than that value. If methane is limiting, then this value will be less than that value. Okay. Rather than going all the way to grams, we can make that decision with moles. All right. So here's a practical example. We're going to do this limiting reactant problem for the synthesis of aluminum oxide from aluminum and oxygen. Now, did I name that correctly? Aluminum oxide? Yes. It's a type 1 compound. Aluminum is always 3+. So it's type 1. All I have to say is aluminum oxide. Okay, we're given 10 grams of aluminum and 10 grams of oxygen. What mass of product will be produced? Okay. We still have to turn these into moles, before we can find out the mass over here. But when we convert them to moles, we've got to determine which one is the limiting one. So I'm going to take 10 grams of aluminum and convert that to moles of aluminum. Right? And the molar mass of aluminum is 2698. Just check it. Yes. 26.98 grams. So that produces, that's how many moles of aluminum? 26.98 into 10 is 0.3706 moles of aluminum. Okay. Let's go ahead and convert oxygen to moles. So 10 grams of oxygen. And what's the molar mass of oxygen? Well, each oxygen is 16, so it's 32 total. 32 grams per mole. So we have 10 divided by 32. And that's 0.3125 moles of oxygen. Now, there's usually 2 or more ways to solve a problem in chemistry. We can determine the limiting reactant right now because we know the ratio of this is 3 to 4. So for every 3 oxygens, you need 4 aluminums. So we could say 3125 divided by 3 times 4 should be 4.166. We need 0.4 moles of aluminum. So aluminum is probably limiting. We don't have enough. Right? That's one way. The other way is to determine how much product will actually be produced and then compare the values. All right, so let's do that and see if my deduction here is correct. So we need to convert this aluminum to aluminum oxide and do the same thing here, only for oxygen, and convert it to aluminum oxide. So this ratio is 2 here and 4 here. So we need to take 0.3706 and divide by 2. So that's 0.1853 moles of aluminum oxide. That's what would be produced if all of the aluminum were consumed to produce that product. How about for oxygen? 0.3125. And let's see, the ratio here is, again, 2 there and 3 here. So I'm going to multiply 2 times that and divide by 3 is 0.2083 moles of aluminum oxide. That's the amount of aluminum oxide that would be produced if all of the oxygen were consumed. Okay, so the least amount is produced, the least amount of aluminum oxide is produced from 10 grams of aluminum. That means, correct, it is limiting. Okay, now that we know what the limiting reactant is, we can determine the mass. From this value, we can determine the mass of that. So 0.1853 moles. And then the molar mass of aluminum oxide is a given 101.96. 101.96 times that value. 101.96. And I get rounded off to 3 places. I get 18.9 grams of aluminum oxide. Okay. Okay. Yeah, there we go. And we convert oxygen also. There, okay. So far, so good. Then we determine how much aluminum oxide could be produced by either way. And we find that aluminum is the limiting reactant. Okay. Then we take that value of aluminum, convert it to aluminum oxide. Well, it's already converted to aluminum oxide. So we just change that to mass. And that's 18.9 grams. Okay. That's how you do stoichiometry when you're given amounts of all the reactants. If there's not a word in there, if the problem doesn't specify one as excess and the other then would be the limiting reactant, then you have to determine which one is limiting. And in this case, we're given amounts for both of them. That means one of them is going to run out first. And that is part of the solution to the problem, is determine what is the limiting reactant. Right? Don't make this mistake. Once you determine moles, you can't just say from the moles that, oh, let's see, well, this is lesser than that one. This must be limiting, right? It doesn't work that way. The limiting one's the one that runs out first. And that's based upon the stoichiometry of the equation, the mole ratios of the equation. That's how we determined that aluminum is the limiting reactant, not oxygen. Okay. So to drive home the point, for this combustion of hydrogen and oxygen to give us water, which of the following reaction mixtures could produce the greatest amount of product? Okay. Let's take them one at a time. All right, if we have 2 moles of hydrogen and 2 moles of oxygen, okay, how much water can we produce? Well, for every 2 of these, we need 1 of those, right? So we've got 1 excess. That means this ratio, 2 to 2, 1 to 1, this would produce 2 moles of water. That first one produces 2 moles of water. Okay. Hydrogen is limiting, producing 2 moles of water. All right. Second scenario, 2 and 3. Again, for every 1 of these, we'll use up this one to produce 2 moles of water. So there we have the same outcome. Now the final mixture is going to be a little different because you've got more excess oxygen. But the product is the same. Now if we have 2 moles of hydrogen and 1 mole, what's that? That's stoichiometric. Stoichiometric mixture. Okay, produces 2 moles. Now, if we have 3 moles of hydrogen and 1 mole of oxygen. So for every one of these, I need 2 of those. So I've got an excess of 1 mole of hydrogen. And this one runs out. But it produces 1 to 2 moles of water. So each one of these scenarios produces exactly the same amount of water. All right. Okay. Let's see. Okay. How many grams of ammonia will be produced from this reaction? This is the Haber-Bosch process. 3 grams of nitrogen and hydrogen, 3 grams each of nitrogen and hydrogen. Okay. And we want to know how many grams of this produced. So let's find out how much nitrogen. All right, 2 nitrogens. 1 nitrogen is 14.01, 2 is 28.02. So that's 3 divided by 28.02 is 0.1071 moles of nitrogen. Now let's go ahead and convert that to ammonia. That's 2 and this is 1. So 2 times that would be 0.2141 moles of ammonia. Now let's do the same thing for hydrogen. One mole of hydrogen gas would be 2.02 grams. Because each hydrogen is 1.01, 2 of them is obvious. So we have 3 divided by 2.02 is 1.485 moles of hydrogen. And we're going to convert that to ammonia. So 3 of these, 2 of those. Okay. So 2 times that divided by 3 is 0.9901. 9901, yeah. Moles of ammonia. Okay. We can see at a glance that nitrogen is limiting. So we're going to say, since this is limiting, we're going to use 0.2141 moles of nitrogen, of ammonia as our outcome and convert that to mass. Oops. Grams on top, moles on the bottom. So nitrogen is 14.01 plus 3.03 for the hydrogens, 1704. So let's see, I got that number in there, and then 17.04 times is 3.65, 3 significant figures, grams of ammonia. Okay, there's the nitrogen moles, and there's the hydrogen moles, and then we determined that that's limiting. Now, we didn't give you all the other calculations here. This is one way to do it. The other way is to say, all right, if this is equal to 1, then 3 times that is equal to hydrogen. So 3 times this is much less than that hydrogen, which means that we got plenty of hydrogen, and nitrogen is the limiting one. So that's another way to determine the limiting reactant. Once we've got the limiting reactant, then we can convert it into grams. 3.65 grams. Okay. All right. Now, as if that weren't a big enough problem, limiting reactants, we've also got the issue of what's the yield of the reaction? And what we mean by that is when we start off with a certain amount of reactants and we calculate what we expect to get as product, that is 100% conversion from reactants to products. As a practical matter, the yield, the amount of product you actually get from that scenario is less than you calculate. So we come up with this calculation, which is another way of expressing efficiency. The theoretical yield is what we calculated in our previous examples. The actual yield is what you measure when you perform the reaction. And we calculate the percent yield by ratioing the two. Ratio the actual yield to the theoretical yield. Actual to the theoretical. Times 100 equals percent yield. Now, you can use mass for your outcome, since that's the, we've been doing our stoichiometry based upon mass, but you can also do it based upon moles, or you can do it based upon the volume of gases. You just have to specify how you arrived at your calculation, because remember, percent is a dimensionless number. It just says parts per 100. So you need to know what parts. Is it moles per 100 moles? Is it grams per 100 grams? Is it liters per 100 liters? So what's the percent yield of product if 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen and excess sulfur via this reaction? Okay, I'm going to leave that up there because we'll need that for the calculation. So if we have 2 sulfurs plus 3 oxygens yield 2 sulfur trioxide, and we're given 1.5 grams of sulfur trioxide actually produced. Okay, from 1 gram of oxygen and excess sulfur. Okay, so we can use this value to find out what is the theoretical yield of the sulfur trioxide. So we need to convert 1 gram of oxygen into moles. Let's see, 32. That's 3.125 times 10 to the minus 2 moles of oxygen. Now we want to convert that to sulfur trioxide. So we need the coefficient ratio. We have 3 oxygens and 2. See, 2 and 3. So 2 times that and divided by 3 is 2.083 times 10 to the minus 2 moles of sulfur trioxide. Then we convert sulfur trioxide to mass. Since our outcome is given in mass, we need to calculate the theoretical in terms of mass also. So sulfur trioxide is 32.07 for sulfur, and then 3 times 16 for oxygens. Okay. That's 80.07. 80.07 times that value is 1.67 grams theoretical. So our percent yield now is actual divided by theoretical times 100. And I get 89.9% yield. That's actually very good. Well, there's a rounding error in there somewhere. The nearest one is 89.8. Well, let's see, did I round that correctly? Yeah. Oh, okay. Yeah. This was calculated to give us a rounding error. Okay. So that's an example of calculating percent yield from a given reaction and its stoichiometry. And we're going to up the game just a little bit and actually work backwards. Let's see how we're doing on time. Yeah, this will be our last problem. Then we'll be done for the day. So we're given this equation, B4 and F2. Let's see, solid and gas. Yield for gas, solid, and PF3 gas. Here's our balanced equation. We want to know, and this actually is a more practical problem. It's one that you would encounter in the real world, right? If you were an engineer for a company and the management says, right, I want a certain amount of PF3 produced, right? Then you would go see what is the efficiency of that reaction that you've determined experimentally. In this case, it's 64.9%. But we need 85 grams of PF3. So what is 85.0 grams? That's actual. That's the actual amount we want to end up with. We need to produce that much, but we need to know how much of this is required. How many grams of phosphorus are required to give us this outcome if we know the reaction, the yield is 64.9%. So what we need is to work backwards. What's the theoretical amount that we would come up with? Then we can do theoretical jump back here. Okay, so let's go back to our equation. Percent yield, in this case, is 64.9%. And that's equal to what? Well, that's equal to actual PF3 divided by theoretical PF3 times 100. Okay. Now, the actual amount we know is 85 grams. So notice what we've got here. We've got an equation in one unknown, so we can solve for it. So let's bring this one over here. Theoretical PF3 equals 85 grams divided by 64.9% times 100. Let's see. Okay. So if we do that calculation, 85 divided by 64.9 times 100 is 130.97 grams. That's the theoretical amount of PF3 that we would use to calculate the required amount of P4. Let's see, how much of this have I done? Okay, there we go. Gotten that far. Okay. Now from here, we want to convert this, since this is excess, we want to convert this to moles so that we can move from moles to moles and back to grams. Okay, so let's convert this to moles. Grams on the bottom, moles on the top. We need the molar mass of PF3. So phosphorus is 30.97 grams per mole, and fluorine would be 3 times 19. So that's 87.97 grams per mole. 87.97 there. And that's divided into 130.97. 1.489 moles of PF3. Now we can use a conversion factor based upon the coefficients. So 1.489 moles of PF3, and we want to convert that to P4. So for every one of these, we need 4 of those. So I divide this number by 4, and we get 0.3722 moles of P4, and we just convert that to grams now. So what's P4 in grams? Well, phosphorus is 30.97 times 4 is 123.88. So I get, let's see, rounded off to 3 places. Yes. 46.1 grams of P4. Okay. So there's the rest of the calculation. 46.1 grams of P4. That's what we need to begin with to produce an actual amount of 85 grams of product. Okay, that's it for today.